write a few formulas, we would need to know these things. So suppose you have some kind of a scatter plot with some trend that you think there should be some regression line where your idea is that the actual value of y is like some a or b0 plus b1 x plus some error. And our assumption is that the error is following like a bell curve. It's a normal distribution. Okay? So that means that this line should be some points on the data should be above this line, some points should be below this line, and they should be kind of bell curve, so that you have more things closer to the linear regression line, stuff like that. So those are some assumptions, and in that assumption, we really want to know what B1 and B0 are. That's what we want to know. So when you do this, this portion is called a linear regression. And we write it as y hat equals to b0 plus b1x. And therefore, y would equal to y hat plus some error. That's the idea. Now, there's also x bar and y bar. I talked about the x bar and y bar when we were talking about covariance. You have all these data points. You can project everything on the x-axis to get the x values, and those values can be averaged out to give you this x bar. All the points can be projected on the y-axis. You get all these y values. You take the average, you get some y bar. And then there's something called the sum of squares. Okay? Okay. So let's rewrite this as y equals to y hat plus y minus y hat, which is a tautology. Right? This is always true for, it doesn't have to be y hat and y. Just to note for the fact that what is E? E is the error between your prediction made by the linear regression line and the actual value observed. Right? So let me write like that. And then we can subtract y bar both sides, and then we get y minus y bar equals to y hat minus y bar plus y minus y hat. So all I did was I subtracted y bar both sides. So we have three quantities. So this portion is our error. This tells you how much the prediction is away from the mean. This tells you how much the actual value is away from the mean. Okay? So let's talk about sum of squares of y. This is defined as summation of y minus y bar squared. And notice that this is really the formula for the variance, except that we didn't take the average yet. If you divide by n, it's going to be the variance. So in other words, the variance of y will be 1 over n, sum of squares of y. Okay? And I think in the literature they like doing it this way. writing it this way rather than dividing by n, because like if you do this, then there's always this question of, is this a sample or the population? And then should you divide by n or n minus 1? That's a bit questionable, so you just don't delete this and then just talk about this, okay? And then sum of squares of regression is defined as sum of y hat minus y bar. And this is, so SS means sum of squares, okay? So sum of squares of regression. So that's what it means, sum of squares of regression. So this is sum of squares of y. It measures how far y is from the average, except that you didn't take the average. Same thing, you didn't take the average. And then sum of squares of the error, which we called right here, this error, is difference between y and the predicted y. Okay? And then you can prove that sum of squares of y is sum of squares of regression plus sum of squares of the error. Okay? So how do you prove that? Well, you just square both sides. And the thing that you have to be careful is that if you square both sides, it's not the square of this plus square of that. There are some cross terms, right? But the cross terms happens to just give you 0. Okay, so aim. Find y hat equals to b0 plus b1x that minimizes the square sum of residual, which is y actual value minus the predicted value square, and you add them up. Okay. And see, these are variables. So to find the equation for the line, that means we have to find the slope and the y-intercept, right? That's all we have to do. So our aim is to figure out what B1 is, what B0 is, assuming that we're given this paired data set, xi, yi. This is given with I equals to 1 through, let's say, n. So let's say we have n samples, and we're trying to find a formula for B1 and B0. That's the setup. Okay. So using this, let's try to write down this formula that we're trying to minimize. This one is called sum of squares of error, because this is the predicted value, that's the actual value. If you subtract the predicted minus the actual minus the predicted, that's called the error, right? So you're squaring the error and you're adding them up. So it's the sum of squares of the error is what I wrote there. But then we're going to replace yi hat by this value we just got. So minus b0 minus b1 xi. We're squaring them. We add them up with respect to I. Okay, as I said, because x and y, xi, yi are sample values that are provided to us, those are fixed, and we're trying to find out the value of b1 and b0. You should really look at this function as a function of b1 and b0. That's how you view it. And this is I think this is a very fun exercise. If you have taken calculus and if you want to, if you're somewhat confident with your calculus skills, just take a sheet of paper and just keep calculating, see if you can get this result on your own. It's very fun. Okay, so we know that if a function attains its minimum, at the minimum, we call that a critical number, critical point, right? At the critical point, all the slopes are what? Zero, right? So we use that. We're going to think of this as a two-variable function, but if it attains its minimum at the minimum point, all the slopes are zero, so we differentiate, we do a partial derivative with respect to b0 of this thing, f b0, b1. And then we know that at the minimum, this has to be 0. Now let's write down what that means. Hopefully you didn't forget your calculus. Just pretend that these are some numbers and this is x. Okay? So if you have derivative, how do you differentiate if you have something nested inside? What rule do you use?
Chain rule.
Chain rule. So think of the entire thing as just x. So you have x squared. When you differentiate, it will be -2. No, positive, sorry. 2 will come down, and you're going to get yi minus b0 minus b1 xi. But then this is nested inside, so you have to bring it outside and differentiate using the chain rule. Inside function must be brought outside and differentiate. So what do you get? This is a constant. We're differentiating by b0, so these are constants.
So those be 0.
Yeah, these will be 0, and this will give you
-1.
-1. So that has to equal to 0. Now let's try to rewrite what this means. I can divide both sides by -2 so that this 2 is going to go away, that -1 is going to go away. And what you get is summation over yi minus b0 minus b1 xi should give me 0. And since summation is linear, we can add them separately and rewrite it as yi minus summation of b0 I, summation of b1 xi I equal to 0, just like that. And by the properties of the summation, this coefficient will come outside, like here, b1. And then this thing, there's no I here, but it's added n times, right? So b0 is being repeatedly added n times. So what would you get? It's b0 plus b0 plus b0 until you reach n, 1 through n, right? So what do you get if you do that? N times
B0.
B0. And now you divide everything by n, because then you have a nice formula. What is adding up all the y values and dividing by n? What is that called? You add all the y values and divide by n. What is that called? Average. So this will be y hat, right? Minus b0. You divide all the xi values and divide it by n, you get x bar. So you have a formula for b0, which is that b0 has to equal to y hat plus, actually, no. If you move this over, y hat minus b1 x hat. Okay, so that's the first result. Now this is not totally satisfactory because it tells us that in order to know B0, you first must know B1. Okay? But this is a nicer equation than the one that you get out by differentiating the second one. So we're just going to have this one, and then at some point we're going to use this to the second one and simplify the second result. Right? So let's now try to calculate the second guy. So for the second guy, we're going to now do a partial derivative with respect to B1. And trying to differentiate this with respect to this B1 still requires a chain rule. This is nested inside this square function, so same story. 2 comes down, whatever that's inside stays unchanged, but then this has to be pulled out and you have to differentiate by B1. Okay, what do you get if you differentiate the inside function by B1?
Negative 1x.
Right, this just becomes B1 integrate, B1 differentiates to 1, so it's negative 1 times xi, right? Or just negative xi. That has to equal to 0. I already know that so I have this one result, right? So what you want to do is you want to put write this one. Now how do I know that second one is true? Because I know that this is true, right? This is true. And if I multiply x bar both sides, that's a constant multiple, so this is still true. And then once I have that, I can subtract the 2. And since these two are exactly the same, I can rewrite this so that it looks like summation of I 2 times yi minus b0 minus b1 xi with minus of xi minus x bar. Okay? All right, now you're talking. So we can rewrite b0. So again, let's get rid of the negative 2. Rewrite b0 from the first part, minus minus y bar plus b1 x bar minus b xi. Okay? Okay. And then just take this much times this one, have a separate summation. Plus, and then this times this with b1 factored out, so b1 factored out, and you have summation of x minus x bar, x minus x bar. And now look, if you divide this by n, if you divide both of the summation by n, what is this? We did that earlier in the class.
Covariance?
It's the covariance of x and y, isn't it? Right. So you get covariance of x comma y. Oh, sorry, I messed up with another one. This is x bar minus xi. So to make it as xi minus x bar, there should be a minus. Okay. So this formula becomes this second one. What is that? What is 1 over n times summation of xi minus x bar squared? What's that? Huh? That's the variance. Or just v of x, right? So now what is b1? b1 is equal to covariance of xy divided by the variance of x. Okay? So that's a very nice formula. It says that the slope of the regression line is the covariance divided by the variance of itself. Okay? And if you actually check the units check out. see, this is the units of x times units of y divided by units of x squared. So this one will have, this will be the unit of y divided by unit of x. And then to this one, in the linear regression formula, when you multiply an x value, the unit for x will cancel, so this overall will have a unit of y, times another something that has a unit of y, gives you the predicted value with the correct units, okay? So that's another way to see that whether this is obtained correctly. Okay? So that's one. Another one is, instead of dividing by n, if you don't divide it by n, then the top one would look like summation of xi minus x bar times yi minus y bar, divided by just summation of xi minus x bar times xi minus x bar. And these have names. The top one is called sum of squares of xy, although it's not a square, they just say it as sum of squares of xy, because it looks similar to this one. This is the sum of squares of x, because this is indeed a square. Okay? So another formula that you would see would be that the slope of the linear regression is obtained by xsxy divided by ssx. Okay? So that's what we proved using calculus. That's all.
So is the quiz moved or?
Yeah, quiz is moved to